Good morning and welcome you all to the NPTEL course Advanced Distribution System Analysis and Operation. We are continuing with our module 2, what is DER Integrated Distribution Network Modeling. So, till now we have seen the model of the DERs, loads, volt var controlling devices, and also the line model for a distribution feeders depending upon their voltage and the current that we represented the ABCD parameter. So, today we will start with the distribution network power flow models, which is mostly used whenever you go for optimal power flow studies or distribution network planning. At that time, we do not deal with the current model or the ABCD parameters. It is better or it is best if you can represent your distribution network powers, that may be an injected power or maybe a power flow in terms of it. So, depending upon that, for distribution network you have mostly two different kinds of power model. One is called bus injection model and the second is called branch flow model. Now, what is bus injection model? The bus injection model or the BIM is formulated using bus level variables. That means, let us say you have a line connected between two buses, let us say this is n number of buses, this is m. Then bus injection model says you consider only this bus, that how much power it is giving or how much power it is getting as an incoming power or how much the load is tapped from there. So, what is the KCL at this bus? Generally that is the basis of developing the bus injection model. So, it says the bus level variables such as active and reactive power injection or current injection at each network bus. So, that is mainly depends upon your KCL equation at each and every node or buses. In contrast, your branch flow model is expressed using branch level variables. That means that will depends that how much power is flowing through the line or the branch. That means your S, N, M. Okay. So, that means how much power is flowing between buses N and M, and that level variables including the active and reactive power flows and the current in the distribution lines are generally considered to model the branch flow model for distribution system. Now, we will see one by one how you can mathematically formulate these models. Before moving towards that, let us do a brief comparative analysis between these two models. First, bus injection and branch flow in terms of primary variables. As I already told, for bus injection it is an KCL equation. So, that means your power injection and the current injection at the each bus level, that will act as your primary variable. Okay, got it? But for branch flow model, normally we are considered about the flow through the line. Okay. So, that is why this branch flow model takes the variable of the power flows or the current flows. Okay. Formulation basis, for bus injection model we considered Y bus matrix, for branch flow model we use normal Ohm's law and the KCL KVL equations. Branch injection model is specially suited for mesh system. You will see when we will derive the mathematical model, it is more or less relevant with the transmission network Newton-Raphson load flow model. So, that is mostly suited when your network is meshed. However, your branch flow model is mostly suitable for radial and weakly meshed distribution network. Numerical stability if you take, then branch injection model is mostly good or it is converged properly for mesh system as I have mentioned, but for radial distribution network, what we consider the distribution networks are mostly radial. For radial distribution network, it suffers from convergence issues. However, your branch flow model is very robust and it converges with the for the radial distribution network. Comparing that, you have complexity, you have computation time, you have unbalanced distribution system on loss modeling. For computation, if you see that your bus injection model needs the computation of the Y bus matrix, that is not required for your branch flow model. So, compared to your bus injection, your branch flow model is good as far as the computation is concerned. For unbalanced system as well, determining the multi-phase or three-phase branch flow model is comparatively easier compared with your three-phase unbalanced branch injection model. So, that is also beneficial for the branch flow model. So, whenever you will see in the subsequent modules also you will see that we are doing analysis on the distribution network, we mostly will follow this branch flow model. For loss modeling as well, the bus injection model inherent takes the bus injection values, that is already addition of the losses, and from branch flow model we take explicitly we take the loss when we take the consideration of the power flows in the line. We will see all these things one by one. So, we will start with the three-phase original formulation of the bus injection model. We will think that it has a three-phase system allowing accurate modeling of the unbalanced distribution network, which is very common for distribution system. That means we have a bus, we have three phases connected with it. So, if this is your bus I, this is your bus J, so this is phase A, B and C. So, we will take a three-phase configuration, and it models the network by directly specifying complex power injections. That means how much is the real and reactive power injection at each phase level. Not only bus level, we are doing it at the three-phase basis, so we will see at the phase level. Then we will do that phase domain admittance matrix also we will see captures the electrical relationship between all phases and the buses in the network. And that admittance matrix we have seen in the last class as well, that will be a 3 cross 3 matrix for each bus, that will consider even the mutual coupling between the phases. So, let us say this is the architecture of line, that means there is a bus number n, there is a bus number m and they are connected via three phases. Each phase will have, this is the amount of admittance, that is your y n m h g, okay, that is equals to your g plus j v. So, h and g that represents the phase indices, that is either a, b or c. V and H represent your bus voltage for bus N and phase H. Current injection is represented by I and H. Your power injection at bus M and phase H is represented by SMH. This is your power, and then this is your complex admittance between bus N and bus M, taking the phase H and G. Okay. So, with this nomenclature we will start the development. So, this is your bus voltage matrix. Obviously, you have n number of buses. If you have, each bus will have three phases. So, total number of elements in the bus voltage matrix will be 3n cross 1. Similarly, your bus current injection matrix will have 3n cross 1 element. Each phase will have a current injection. Your bus admittance matrix will be a 3n cross 3n. You have total n cross n number of buses. Each bus will have a 3 cross 3 admittance matrix. So, total admission matrix size is 3n cross 3n, where each of the element represent a 3 cross 3 matrix. Okay. Now, with this, if we see the complex power injection, that means how much complex power we are injecting to the bus number M, that we can see the power is voltage multiplied with the complex conjugate of the current I. That means V multiplied with I star, and that multiplication is actually element wise multiplication. So, if we expand this equation, we will get S equals to, this is the power for the bus M, three phases. You will have SMA equals to VA into IA star, SB equals to VB into IB star, and VC equals to VC into IC star. So, that is why we do it as a element wise multiplication. Now, current, nodal current equation is your current I is equals to your admittance into voltage, that we know, that V equals to I into Z, right. So, I equals to your V by Z. So, 1 by Z is your Y. So, you can write it I equals to V into Y. So, that we have written here. So, put this I value to this equation number, let us say this is your equation number 1. So, put that to the equation number 1 and we will get that S equals to V element wise multiplication of Y bus and V of complex conjugate. So, with this equation, if we expand this equation in a per phase basis, then we will get it is a matrix. So, if you do the matrix multiplication and addition expanding that matrix formula, you will get that summation of n equals to 1 to capital N, then summation of the total phases, admittance matrix for the current and then for the voltage, what we wrote over here. Y bus into V, the same thing we wrote here, that your Y and your V. If you add both of them, then you will get the current what you are feeding over here. Okay. So, the same thing we will do with the current as well, power as well. So, the SMH, that is your apparent power, is equal to your active power plus your imaginary J multiplied with reactive power, that is equals to your voltage and the current complex conjugate. Put this value to this equation and you will come up with this equation. So, this is VMH complex conjugate of summation of this term. Okay. Now, let us say everything, voltage, current, everything is a complex quantity, right. So, represent this voltage at a magnitude of VMH and an angle of e to the power j delta mh. Okay. That means, it is a VMH angle of delta mh. Okay. This one. Similarly, you have VNH, also your bus admittance you can write like y angle theta. So, that in rectangular coordinate conductance plus susceptance. Okay. Now, put all these things in your previous power equation and will expand. So, Ynm will put this theta quantity, Ynm magnitude and e to the power j theta hg with this voltage value, this is your Vng. So, this will come as Vmh, this is from the magnitude, this magnitude is here, this magnitude is here. Now, the angle part, angle of Vmh is delta mh, then you have complex conjugate of it. So, Vng star, Vng is Vng e to the power delta nh. So, star means complex conjugate means you have minus of it. Similarly, you have Yn, y quantity, that is actually the angle is theta. Now, you have complex conjugate. So, this will become minus theta. So, this is your total power equation. Now, if you split that into two parts, that is your active power and the reactive power part, then what will you get from this equation? This is your e to the power. So, e to the power j theta, you can write it as a cos theta plus j sin theta. Theta means your total delta m minus delta n minus theta nm. Okay, right. So, this you can write it like this. So, if you separate the real and the imaginary part, then your active power injection to the bus m of phase h is summation of n equals to 1 to n, that means total bus summation, total phase summation, magnitude of your sending end voltage, your admittance matrix, admittance component magnitude, your receiving end voltage magnitude and cos of the angle difference. Similarly, the same component will be there for Q, just your angle will become sine. So, this is your original 3-phase BIM. Depending upon how many phases you are considering, this is your 3-phase BIM. So, if you expand it further, that this Ynm, this quantity, this is actually your Y is what? G plus JB, that means conductance plus susceptance. If we put this value here, then we will get to the initial equation, it is a Ynm conjugate. So, if we put, then that will be G minus JB, rest of the part will be same and just do the multiplication. And with that you will get the equation for the BIM in terms of the line parameters, that is your conductance of the line and susceptance of the line. That means your admittance quantity. Depending upon this quantity, you will calculate how much active power and reactive power will be injected to the each phase of a particular bus. So, this is actually BIM with line parameters. Clear? Now, if we reduce it for the single phase basis, that means for a balanced system, this is for your 3-phase system. If we go for the single phase system, then we will see for balanced system each phase is separate because you do not have any mutual coupling, that means off diagonal elements for the Y matrix is 0. So, if you put that, then you will get the 3-phase injected power equation will be revised for a single phase format, and then you will get this PM and QM equation. Now, you can see the resemblance of this two equation with the actual Newton-Raphson equations, what we normally used for the transmission network. So, bus injection model is more or less same for both distribution network and transmission network, but you have to keep it in mind that for transmission system that is a single phase model, because transmission system we considered as a balanced system. But for distribution network, if you really want to consider the unbalancing effect, then you have to take this equations where you have mutual coupling components. This Hg, that is the mutual coupling between two phases of two bus. That means this will represent that the mutual coupling is there between phase H of bus N and phase G of bus M. So, these mutual couplings you have to consider if you go for unbalanced network model. So, what is the problem with this 3-phase non-linear BIM model? First thing, your original bus injection model is non-linear, that we have seen, right. You have cost term, you have sine term and multiplication of this 2 component, voltage component, you do not know the voltages, right. So, multiplication of 2 unknown, that is also a bilinear term. So, we call it a non-convex equation or non-linear, because it will possess as a v square or something x1 x2, these are all non-linear equations because the order is 2. Same you have cos and sine terms, these are highly non-linear terms. So, the original equation is non-linear. So, if you include this kind of equation in any problem solving or distribution network analysis problem, your computation complexity will be huge. That is the first reason. Second, already you have 3 phases with mutual couplings, that means you have already so many variables you have to deal with. Now, imagine that your network size is also very huge. A typical network IEEE 8500 bus network, it is an unbalanced network. So, if you have an 8500 bus network and you have to take it as an unbalanced network, you cannot imagine the size of the problem you have to solve. Huge number of variables, huge number of parameters. So, dealing with this kind of unbalancing BIM model for large system is very difficult. That is the first thing. If you want to get rid of this complexity, the only way that you can linearize the nonlinear expressions, that will make your problem solving more faster and more tractable. So, how we will do that? For that, we do the linearization of the bus injection model by making the real time system monitoring and decision making feasible. If we do with a adopting proper linearization technique, that will make your non-linear problem convert to a feasible linear problem. So, but you have to keep in mind that linearization techniques you are adopting for representing each and every non-linear component, that linearization has to be perfect. Otherwise, your deviation from your original solution will be very huge. That means, you are compromising with the accuracy of the result. And if that happens, then you cannot adopt that linear model, because always whatever result you will get anywhere, anytime, that result has to be close to your original equation. If it is close, if your accuracy is at the level of 98% or 99% or 95%, then that result is acceptable. But with the linearization, if your accuracy has reduced to 50%, then that linearization technique is not acceptable. So, that we have to keep in mind, and considering that as well, we have to linearize our bus injection model. So, how will linearize? First, we have to take two assumptions. These assumptions must be physically feasible as well. First assumption we will take that a small voltage magnitude deviation from the nominal voltage. That means in case of per unit basis, keep in mind this is not in the actual unit, that is in the per unit basis. So, that means actual bus voltage is somehow close to your 1 per unit, but little bit of deviated by del V. This is quite acceptable because all the time when we talk about voltage stability, or we want the system to be close to its nominal value to maintain the systems in a stable operation. So, this assumption is feasible even if you go with the standard of ANSI or IEEE. They also says that your voltage should be as close as of your 1 per unit level. So, keeping these standards and the real time operation, we can think this assumption is good. Then the second assumption is small voltage angle deviation from the nominal value, that is 0 radian. That means actual voltage angle is 0 plus somehow some small perturbation. That is also true. As you have studied in stability, rotor angle stability, we always keep the rotor angle difference between two buses will be almost 0, close to 0. Now, you start with the slack bus, your slack bus angle is already 0. So, you are trying to keep the bus angle of the next bus of the slack bus close to 0. Similarly, the next bus close to 0. So, always we will try to keep the angle difference and henceforth the angle of the each and every buses close to the 0 value. So, keeping these two assumptions, now we put at the cos and sin. We know cos of a small angle gives the value of 1 and sin of a small angle gives that entire value. Like this is your cos of 0 plus delta del delta, and this is your sin of 0 plus del delta, right. So, cos of 0 plus del delta is close to 1 because this is almost going out and this is equal to your sin only angle delta. Now, we put this on these equations of the voltage and we will see that Vmh is 1 minus del Vmh and angle, this cos term will become 1. So, 1 plus j of delta del delta. Now, neglecting this, doing the multiplication and neglecting this 2 multiplication of 2 higher order terms, we will neglect that and we will come to this simplified version. Similarly, for bus number n as well, we will get the same expression. Now, put this expression values for the injected bus equation for bus m and phase h of the same equation. We will put that the same Vmh will be 1 minus del V plus j del delta, and then for Vng we will put this equation. Now, we will try to simplify them. So, this is your original equation we got here, and then you multiply at both the side like this, you multiply here, you will get this term and then this term. Then again neglect the higher order terms, that is multiplication of this and this, this and this, this and this, and this and this. If you neglect this higher order terms, then you will be only with 1 minus del Vm summation terms, then this term, then only your single del values terms. So, y nm hg del of Vn minus j y hg star del of del delta plus your this term j of del delta summation of y hg star, means this equation. Okay, got it? We just eliminating all the second order del equations, del expressions. So, same thing, we will do the again multiplication, we will just keep this term inside and do the multiplication, and then you combine this third and fourth, means this is your third term, this is your fourth term, combine this together and you will get the simplified version like this. Okay. So, this is your YHGNM 1 minus del V plus YGNM star 1 minus del V into del Vn, and here also you have YHGNM star 1 minus del Vm multiplied with del Mh minus del Ng. Okay. So, you have finally this equation. Now, we can further simplify it. How? Here you also again see there is a multiplication of two higher order terms. Two first order, if you multiply them you will get a second order term. Similarly, here as well. So, the same term again we can represent like this, that 1 minus del Vm multiplied with del Vn will be this term you can neglect. So, this is only del Vn g. Similarly, this two multiplication you can neglect and this will come only as del Mh. Similarly, del delta Ng multiplied with 1 you will get only del delta Ng. So, if you put these values in the last equation, then you will get Hg star YHg del Vn minus del Vm, then summation of Ng with the j term like imaginary term YHg star del m minus del n, del delta n. Okay. So, now put the complex conjugate value of your y, that means the bus admittance quantity, and if you put that, then this is your final simplified equation. YHg star, here you will put that and you will get g plus jb, g minus jb. These two terms are replaced in this equation and in this equation. We are not putting it here. Why? I will come to that. So, these two equations we have put, we got y multiplied with del Vn minus del Vm and then y star minus del delta m minus del delta n. So, this is your overall, if you split this equation for Pm and Qm, keeping the real and imaginary part, splitting them, you will get your Pm will be summation of this, means this term plus your complete this term, that is the summation of the buses, phases and your G term with the voltage difference and B term with the angle difference. Similarly, for Q we will get B with voltage difference and G with current difference. Now, this term if you see in the per unit level, this term is quite small. Okay. So, that you can neglect and consider it to be a close to 0, not exactly 0, but you can consider it to be a close to 0 value. So, by neglecting this term, now you can see the active power injection for bus M and phase H, it is summation of buses, summation of phases, G means conductance between the phase and the buses, then del Vn minus del Vmh, del Vng minus del Vnh, then susceptance and del delta Mh minus del delta Ng. Okay. So, if you do this, then your Qm is also minus and this. So, here you can see the order of the variables all are 1. So, you got an equation after taking those assumptions, you simplified it and you got a equation finally which has the variable with order 1, which was previously of order 2 and also with the sine and cos term. So, now these things you have omitted from your bus injection model. So, this equations has become now linear, and solving a linear equation is a easier thing. So, with this I will complete today's BIM lecture and we will continue with the branch flow model in the next lecture. Thank you.